Right. So the way we're going to do this is we're going to go through. So the topic, of course, is CNNs, convolutional neural networks. And also, we do realize that the lectures haven't covered CNNs in full. So this recitation, I feel, should be useful to you even through the next week, the next couple of lectures, and especially the homework 2 that has been released. So the way we're going to do this today is we'll go through the forward pass first. Um, we'll go through the backward pass next, and then we'll quickly gloss over this tutorial notebook that we've created for you. And that notebook just says, hopefully this recitation should help you throughout the homework. So it has a lot of different sections, but we'll go through them. Right. Okay, I will share my screen. Please let me know when the slides are visible.
You can see the slides.
Yeah, perfect. All right, just give me 1 second here. All right, so as I mentioned, the topic is convolutional neural networks, and we will slowly and steadily go through the forward pass. And hopefully, none of this confuses you too much, because one thing I realized while making the slides is that CNNs tend to blow up in complexity like that. So if you're not careful when making those jumps from different input sizes and channels and dimensions, it can get very confusing very quick. So I will try to pause at reasonable points throughout the presentation, and please shoot me your questions then, because otherwise I think it might be hard for me to notice since I'm presenting the screen. Right, so with that, let's move on to what CNNs concern themselves with the most, which are usually images. I mean, of course, we can have 1D versions, which go through one-dimensional time series data, but let's stick with images for now. So what is an image? Culture may tell you it's 1,000 words. And for computers, it's not that far off because they tend to look at images as a lot of these different pixel values. And just for simplicity, we will dumb this image down a little bit. So this is kind of what a computer will see when it looks at an image, except not yet. What it sees are numbers, and the numbers tend to represent pixel intensities. How brightly should a pixel be lit up? So on a black to white scale, so for example, 0 being pitch black, 255, which is usual maximum pixel value, being the brightest white it can be. Except it doesn't really see this blurred image either. It just really sees a matrix of numbers, and it interprets them as being this image, right? So what is an image? It's basically a matrix of some dimensions wherein each element of the matrix represents the pixel intensity at that point, right? So of course, images aren't just black and white. And as most of you will know, most color images are produced by at least 3 channels, red, green, and blue. And varying the amount of red, amount of green, or amount of blue there is, you see a different color at each pixel. And of course, the whole image tends to take its color. So really, each color image is a 3-dimensional matrix, where in the first dimension, it's a channel, and the second and third dimensions are its size. And now each element of the image, which is IC, IJ, is basically the intensity at pixel IJ for channel C, right? So we have seen MLPs before. And essentially what MLPs do is they transform one vector into another vector. Now the vectors might be single unit, as in they might have just a single element, but that still counts as a vector. So essentially, multi-layer perceptrons transform a vector into another vector and do some computations in the middle. CNNs, on the other hand, usually take a feature map and transform that into another feature map. And once again, they do some computations in the middle, right? We will, of course, dig deeper into what this means. But essentially, put head to head, this is the only difference between a CNN and an MLP, right? Now, of course, we don't just deal with single channel. We usually deal with multiple channels. And one thing to keep in mind is that each layer of a CNN takes a multi-channel input, which might be a bunch of different channels in an image, and transforms that into maybe the same number or a different number of channels of a different sized image, right? So an image is a very convenient way of thinking of these feature maps, essentially. But again, we'll dive into a lot more details about what happens in a multi-channel CNN. But a quick check, any questions at this point? All right, that's great. Cool. So what does a CNN have? Well, essentially, of course, it has an input, which we will denote as A. And here, for simplicity, we've taken a single channel input. It has a kernel, which is, a kernel and a bias, which is essentially its version of a weight matrix. So we multiply this kernel in some way with the input, and we produce an output. And a convolution is usually represented by a special symbol. It may not always be the circle and a cross inside it, but that's the usual way of showing it. So essentially, we convolve the weight matrix with the input and add a bias to it. Now, of course, that doesn't clarify things. That doesn't tell you what a convolution is. So we'll go through it step by step. Essentially, it's an element-wise multiplication and summation. So, of course, we'll go through an example and that will make it a lot clearer. But essentially, we place this kernel matrix over the input at every point that it can possibly be on. We do an element-wise multiplication, and then we add the bias to it, and then we get one element of the output. So it kind of looks like this. So you take this weight matrix, you place that on the input, you multiply them element-wise, and then you add the bias to it, right? So this bottom right of the slide here shows you what the computation looks like. You multiply A11 with W11, A12 with W12, and so on, and add the bias to it, and you get element 11. You move the weight matrix over one element to the right, and then you get element 2 of the output. Similarly, you get element 3, you get element 4, 5, 6, or 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. Now, once again, for human interpretability, we've kept all the indices as 1 indexed, but when you're coding it up, it will be 0 indexed, so be a little mindful of that. And when you do hopefully go over these slides later, pay attention to how the indexing is changing as we generate the next output in a CNN, right? Okay, quick update. Any questions so far? All right, sweet. Okay, so you might have noticed that the output size changed. I mean, it's not surprising. The output size also changes in an MLP, but in CNNs, there's usually a very nice way of finding out what the output size should be of once I'm done processing the input. So the output width, and the same goes for height, is really the input width minus the width of my kernel, plus twice the amount of padding that you add, true divide by stride, and then you add 1 to it. Now that's a lot of different elements right there, but we know what an input width is. Here it was 4. We know what the kernel width was, and here it was 2. Right? We did not have any padding here, and we did not have any stride here. We'll go through what these things are, but if you just do this quick calculation, you'll find out that a 4x4 image with a 2x2 kernel turns into a 3x3 output. But let's focus on these two things in bold for a second. So the padding and the stride. I mean, as I mentioned in the convolution we just did, the padding was 0 and stride was 1. So when you plug these numbers in, you should get 3. Now, what is padding? I mean, we've done this in homework 1. Essentially, you add zeros. I mean, it can be any value, but 0 tends to be convenient. We add zeros before and after the 1D input that we had. In images, we can pad them on the top, on the bottom, on the left, and on the right. So you can get padding on all four sides of the image. And of course, this extends to channels. You can pad all the channels on all four sides, right? But what does padding solve really? So if you notice, the top left element of my matrix here of the input and the bottom right element of my weight matrix, my kernel, never interacted with each other. Because when I strided over, when I slid my weight matrix over the input, it shifted right and the top left element was no longer in consideration. Similarly, the bottom right element never interacted with the top left element of my weight matrix. And the same thing goes for the whole top row never interacting with the bottom row of my weight matrix, the whole bottom row never interacting with the top row, and so on and so forth. And this is kind of sad. We are letting go of some matrix interactions, kernel interactions possible. How does padding fix this? Again, real quick, padding helps you increase the output size. It preserves, you can have it preserve input size. And of course, you can get a lot more kernel interactions. So let's see how it works. Okay, so this was our regular convolution. And this is what it looks like with padding included, right? So essentially what happened is when we placed this weight matrix on the top left of this padded input now, we got this element Z11, which was created by letting W22 interact with A11. And similarly, the bottom right element of my output map was created by letting weight 11 interact with A44. Right, and the convolution follows the exact same procedure. It's just that my input now has a bunch of padding around it, right? So very quick, if we go back to the formula we mentioned about the output width, I mean, it's clear to see why adding padding would increase the output size. And you can solve this equation to make sure that your output width is the same as your input width, which usually says that your padding should be true divide of your kernel width by 2. Right, any questions so far?
Can I ask a question?
Yeah, please.
So in the previous slide, where you started explaining about padding, if you don't mind, can you please explain again why we are using padding? I was not able to.
Okay. So if you pay attention here, right? And in fact, I can go even further back where we were doing the convolution. So this is where we started, right? We placed this weight matrix over this section of the input. And then we did an element-wise multiply, and then we added the bias and we generated the output, right? The next step was to move the window over. The next step was to move the window over. And once this was done, we moved down. And essentially what happened is these two elements never got to interact with any of these elements, right? They only got to get multiplied with the upper weight matrix, like the upper row of the weight matrix. Similarly, if you notice, the leftmost column of my input never got to interact with the rightmost column of my weight matrix, and so on and so forth. And the bottom row never got to interact with the upper row, right? This was just taken as two extreme examples, which would kind of make it clear. And now what we do is the moment we add these zeros around it, and now we convolve this large padded input with the same weight matrix, we get to place this weight matrix on the top left of this padded input now, and now my bottom right element gets to multiply with the top left element of my input, and vice versa for the bottom right with the top left, right? And then we get these elements here. Does that sort of make sense?
Yeah, thanks.
Yeah, no problem. So now the emoji is happy because everybody gets to interact with everybody, and we have some feature map outputs. Of course, there is some amount of redundancy which the zeros introduce, but it tends to be more in favor of letting you have more kernel interactions. But of course, you need to be mindful about how much padding you give, because sometimes reducing the size of my output feature map is the whole point of doing convolution. So yeah, we just need to keep that in mind when doing all of these things. Right. Any other questions before we move on to Stride? Sweet. All right. So The S there, what is a stride? Essentially, stride talks about how large of a step you're taking. So if you remember what we did before, essentially we move our kernel matrix moved one element at a time. When we were moving right, it moved one element to the right. And once it was done doing the whole row, it moved down by one element, right? So when we have stride equals 2, essentially what happens is it jumps 2 elements to the right instead of jumping one. So we create one output the same way we created the first output before, and the next output is created by striding 2 to the right. Right? So we never covered 1 2 1 3 2 2 and 2 3. Instead, we directly jumped to 1 3 1 4 2 3 2 4. Right? And then similarly, we jump 2 down, and then we jump 2 right. And that's it. That's our output map. So again, with a higher stride, your output map tends to be smaller, which once again goes back to the formula that we had for calculating output width, which is as you increase stride, your output width would naturally decrease. Right? Before I take any questions, I'll take a few slides which Aparajit made for last semester, and they were really great, and I was too lazy to make these again. But they would sort of explain how you can interpret having a higher stride, or how you can do it by simple CNN operations like convolutions and maybe downsampling, right? So essentially, when you have stride 1, you get the output on the left, and you can do this in your own time. It's a good practice anyway. And when you do stride 2, you get the output on the right, right? The way you can really turn one into the other is you can always stick to a stride 1 output, and then you can just remove the intermediate elements and then get a stride 2 output. Does that make sense? Any questions? Sweet, I'm going to take that as a resounding no, and we're doing great. All right, cool. Now comes the part which gets quickly complicated, so make sure that we're paying attention, right? So what really happens in a multi-channel CNN? So these are the things you should keep in mind as we go forward. And intentionally, I tend to go back and forth between the terms kernel and filter and weight matrix, because they always refer to the same thing in terms of CNN. And a bunch of literature will call it kernels, a bunch of literature will call it filters, some literature will call it weight matrices. So I hope you don't get confused by these terms. So essentially, there are 3 or 4 key things to keep in mind. One, you have as many input channels for your filter as you have input channels in your, input image, right? Each channel of the kernel convolves with the corresponding channel of the input and produces some output map, and all the output maps produced by all the different channels get combined into one output map per filter. So the number of output channels that your convolution will have will equal the number of filters that you have. Of course, this will become clear once we go through an example, but it helps to keep these things in mind as we're going through it. So to summarize, we have some number of input channels. Each kernel that we define will have as many input channels as the input image does. And the number of kernels defines how many output channels we'll have after the convolution is done, right? So let's look at an example here. So of course, let's say for now we have a single channel input, and then we have the same kernel and the bias, and then we create one almost output map. Now, something to notice here is I've added one extra dimension here. I understand these are pretty small, but I will enlarge them at some point, and you'll see it a lot clearer. But pay attention to the fact that I now have another indexing going on here, right? So there is one filter for the blue input channel, right? And one output map for the blue input channel. We add one more input, and our kernel gets another weight matrix given to it, of course, and another bias given to it. And then we create another output map, which corresponds to the green channel. Similarly, we create one for the red channel. Right? And we are not done yet, which is why they're called almost output maps. Almost output is not an actual term. I made it up. But the reason why we call it almost output maps is because we need to combine all of them, and then get one output, right? So in summary, we had 3 input channels. Our one kernel had 3 channels which correspondingly convolved with the channels of the input, created 3 almost output maps, and then we added them element by element to create the output map, right? Now, how does this work if we have more than one kernel, right? Well, it kind of looks like this. So what happened is we have 2 kernels. Each kernel has as many input channels as the channels present in the input image. And the number of kernels corresponds to the number of output maps that you get, or the number of output channels that you get, right? One thing to pay attention here, and this was the enlarged part I was talking about, the indexing here is a lot different than what we had before. Before we had just 2 pieces of indexing going on in the weight matrix. Now we have 4. So in a multi-channel input and multi-channel output sort of a convolution scenario, our weight matrix is actually 4-dimensional. The first dimension, and this is completely arbitrary, you can change it as per your calculation, but at least in this example, the first dimension corresponds to which kernel we're talking about. So all of these are 1s, this bias is 1, and they correspond to the first output channel that you create, and hence this output corresponds to output 1, right? Similarly, the second one has 2s in the first dimension, and so does the output, right? The second dimension here corresponds to the input channel that you have. So this one is B, the one behind it is G, the one behind that is R, which is usually represented by numbers. But here for, I think, simplicity, we chose the letter B. Similarly, there's B here, G here, R here. And the next 2 sort of just go through your regular matrix indices, right? And the same thing happens for each of the 2 individual output maps as we did here. I sort of skipped this almost output step for brevity. And essentially now what happens is our convolution, which is the equation that we saw on the first few slides, which is Z equals A convolved with W added the bias, now essentially gives this whole output. So we have a 3-channel input here, which is our input matrix A. We have a 4-dimensional weight matrix called the kernels, which is a combination of weights and biases, which have as many input channels as the input image. And the number of kernels correspond to how many output channels you get after the convolution. And now your output channel has as many channels as the kernels. And of course, the equation of the output width still holds. The one of input width minus the kernel width plus twice the padding, true divide by stride, whole thing plus 1. And you can check the same thing will still hold. And the underlying assumption here is that we still follow the stride of 1 for simplicity. Right, that was a lot. Any questions? And at any point, if you think I'm going too fast, please don't hesitate to stop me. Yes, Kevin.
Are the responses for all 3 channels in each of the filters, each of the set of 3 filters combined to get C?
Yes, for each
Okay.
of the channels. So if we go back here, or maybe if we go back here, assume the same process happens for each of the kernels, and you convolve these 3 input channels with these 3 weight matrices, add these 3 biases, you get some 3 almost output maps for each of the kernels, and then you combine them to get the upper output map. And you follow the exact same process for the bottom one, and then you get the output map for the next kernel.
So it's as if you're convolving a tensor, a 3D tensor,
Yep,
and you're
exactly.
not padding the color dimension. Okay.
Exactly.
Right. Thank you.
Right. And since you brought it up, I might as well mention, of course, this can happen like that in one dot product, which you will have to do in homework 1. And it is super cool. it can be a little annoying to kind of work the dimensions out if you're not used to working with them. But once you work it out, it will be more or less beautiful if it doesn't become annoying first, hopefully. So yeah, for explainability and simplicity, I decided to do this sequentially. But of course, this can happen in one shot and you get your whole output, which is why CNNs are really, really efficient and really quick at doing their computations. Right. There is one more thing we need to mention, which is pooling. Essentially, what pooling does is, if you've ever seen like a CNN map or a diagram, you will have seen a pooling layer usually following some amount of convolution happening. And the reason why we do pooling is to sort of introduce some amount of invariance to jitter, some small changes that might, variances which might happen in your image, some pixel fluctuations, and it kind of takes care of that. Of course, pooling can also be used to reduce feature map size. And there are three major ones. I mean, there can be a whole bunch of others, but even out of the three major ones, max and mean tend to be more common, and max tends to be even the more common out of those two. So we can quickly look at a couple of examples. What a max pool does, and here we're doing stride 2. What a max pool does is you essentially have like a 2x2 window. You place that over your input, and then you extract the maximum out of all the elements that you've seen, and you place that in one output map, right? And you do that for as many times as you need to, given your stride and your output, your kernel size. And the output width equation still follows the same rules. So you have kernel width of 2, we have input width of 4, there is no padding, and there's stride of 2. So we get 4 minus 2, true divide 2, which is 1, plus 1 gives you 2. And then you get a 2x2 output here, right? And if you replace the max operation with like an average mean operation, you get a mean pool or an average pool. So here, hopefully, if I didn't do the calculations wrong, the first element here, which is 9.5, should be the average of these 4 elements here. 4.75 should be the average of these 4 elements here, and so on and so forth. 7.75 should be the average of these 4 elements here. So if you just give it a little bit of thought, what happens here is even if these 3 pixel values, for example, in this blue map here, change by a 1 point here and there, we were not able to transfer data properly, we missed out on some pixel intensities. Even so, the maximum will not change as often. So it will sort of introduce some amount of resilience in your network, right? And similarly, we hope that the mean doesn't change either. And of course, I mean, you would have noticed that the operation that you put here is sort of arbitrary. You can put mean, median. If you want, you can put mode. You can have some weird calculation, which is square of first element, cube of second, and the 10th order polynomial of the third and fourth. I mean, it's really up to you. But hopefully you don't go that far, because it will sort of take away the idea that you're introducing jitter invariance, which is why max, mean, min tend to sort of work well. Right. Before we move on to CNN backward, any questions I can answer? All right. Oh, well, I had a question for you guys. Can anybody tell me what happens to channels when you do pooling? So when we did convolutions, the number of output channels was the number of kernels that you had. What about in pooling? Oh, all right, it's not that hard. Pooling essentially preserves the number of channels, right? So you pool channel by channel, and then you get an output, right? All right, on to backward. Take it away.
Thank you. So let me share the screen and go to the backup part. Okay, so I think we have not covered all the sections in our CNN lectures yet, so don't worry if you cannot understand some details, the backward part, because it's somehow complicated. And okay. So in the backward propagation of convolutional neural networks, we always had the derivatives of the loss with respect to the output of this current layer. So our main issue is to calculate the derivatives of the input of the current convolutional layer and the weights, and the derivative of the weights of the current layer, convolutional layer. So let's consider this example. This is a very easy one because it only has strike one, and the size is pretty small. So your output, as Abu discussed before, it's run by sliding the kernel on the input map, and then do the dot product and place your output to corresponding position. So this is a simplified convolutional neuron. It has two input. The first one is the filter itself, or the weights itself, and the second input is the input matrix, or for 1D CNN and ACN is some vectors. And your output is the convolutional result, is the affine calculation of the current convolutional layer. And for the derivative with respect to the filter, first we have a chain rule like this. So the derivative of this filter equals dl over do times do over df. This O is the affine output of the current convolutional layer, and L is the just the loss. F here is the filter, and if we go deeper, for every element inside this filter, it will be a summation, and I will explain why we need that summation. So let's take our previous example and expand this calculation. So the left bottom part is the actually the convolution calculation. And if we expand this summation, we can get the equations on the right. And this is actually get by extracting so for this F11, we can extract all the related terms on here, 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 here. So this F11 filter is actually calculating all these four output items. So in the backward propagation, we need to consider the gradient contribution of all these four outputs, and that's the similar thing for the remaining filters. So you need to consider that each filter will be considered in the calculation, in the convolutional calculation for more than once. So you need to gather all the gradient contribution from all the values from the next layer. So we can further simplify the second term, like in here, 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 here because as we discussed before, the convolutional layer output is done by doing a convolution among the weights at the input and maybe some bias. So this derivative of output with respect to the filter is actually the x itself, is actually the input of this current layer. So we can further simplify it to these equations, and that will, and this one is what we already have, because when we calculate the current layer, we always have the derivative of the layer next to the current one. So we now have both terms, and so as you can see here, the indices of this first derivative part and the indices of this x part are corresponding. So this is pretty similar to the the convolutional part of our forward algorithm. So we can see that the derivative of filter is actually running a convolution between the input map and the affine derivative output, the output affine derivative map. So this is so let's move on to the loss with respect to the input, and we are also talking about the strike one situation for now. And so for every element in the input, the backward calculation looks like this, and let me explain why. So as we've seen before, the output map is calculating by running some dot products. So we can also extract the contribution of each x. So for example, this x22 is here, 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 here. So the gradient of this x should be the summation of this should be the summation of the gradient comes from this O22, and it's because this x22 is multiplied by the f11, so you need to use so you need to use the chain rule here, and that's also the same case for this O21, O12, O11. And for this x21 example, x21 is here, here, here. So now you only need to consider the O11, O21, and O22. You don't need to worry about this O21. I'm sorry. It's here, here. Yeah, only these two. So you don't need to worry about the O12 and O22. You only need to run the backward calculation and sum them over these two terms. And as we discussed, as we will discuss in the lecture, the derivative with respect to the input is could be done by first rotate the filter, and that's because when we look at the indices of this this is the affine derivative map here, and the indices of the corresponding future position here. It looks like they are the position of them are somehow flipped, especially for the future. So when you calculate the left, the top left value of the so when you consider the top left value of this affine derivative map, you are multiplied by the bottom right value of this future, and you can discover this pattern in every backward propagation in the input derivative calculation. So in order to simplify the calculation, we can simply filter, or we can simply flip the filter horizontally and vertically. So when we do the backward propagation, we can run the convolution on this flipped filter. This is actually the flipped filter, and this is the loss gradient that actually comes from the affine output of this convolutional layer. And notice that you need to pad this affine derivative map before doing the calculation to maintain the output shape. So this is the straight one example, and let's first sum up the straight one backpropagation. So in order to calculate the derivative of the filter, you need to run the convolution on the input x and the affine derivative map. In order to calculate the derivative of the input, you should run the convolution on the 100-degree rotated filter and the affine derivative map of the current layer, this term. And when it comes to the backpropagation in the convolutional layers with stride larger than 1, and let's consider another example like this. So we have a 5x5 input map and a 3x3 filter. So if we set the stride to 2, we will get an output map like this. It's only 2x2. That's because we are calculating the output like this. We are move 2 position instead of 1 when we are sliding the filter on this input. So the each element of in the output map will be calculated like this, and so the let's first discuss the derivative of the filter in this case. This is the right one is the affine derivative map, and this is the derivative of the filter itself. And the equation is similar as the straight one situation. So we also need to run a summation for each future item when we calculate the derivative of it, because it is contributing to many calculations, and we need to consider all the gradient contributor. So in this example, when we calculate the derivative of f00, f00 is calculated was calculated at the fourth time. So it's multiplied by x00 here, x02 here, x20 here, x22 here. So when we calculate the derivative of this f00, we need to sum all the related item. So the loss of this f00 will be the loss of y00, and the loss of y01 times x02, the loss of y10 times x20, and the derivative of y11 times x22. That's the gradient of f00 item. So you can do the similar thing for all other filters, all other items in the filter, and that's similar for f11 and f22. So, but remember that when we do the forward propagation with strides greater than 1, we could first do the normal forward propagation by sliding one position each time, and then dropping some values based on our stride settings. Because when we slide 2 positions in each step, we are actually dropping the output of the intermediate values. So that is when we generate the output. And when we run the backward propagation, you can choose to directly calculate the gradient based on these 4 values, or you can also somehow restore the stride information. But because these positions are actually have no meanings, because you dropped these values when you run the forward propagation. So you can first dilate the output gradient, the affine gradient, with some zeros inside, and then use this dilated affine derivative map and see it as a straight one example, and then apply the previously discussed methods to calculate the derivative with respect to the filter. So this this affine derivative map is actually after the padding, because we are seeing these zeros here. This is the input map. So as we discussed before, the loss with respect to the filter could be done by running a convolution between the input x and this derivative and this affine derivative map. So after these kind of dilation, this is the final output when the stride is greater than 1. And as for the derivative with respect to the input, this is also the same equation that we have seen before. You need to consider the contribution of each position. And let's take this x22 example. So x22 participated in 4 calculation when doing the forward calculation. So when we're doing the backward calculation, this the derivative of this x22 should be the summation of this derivative of y11 times f00, the derivative of y10 times f02, the derivative of this y01 times f20, and the derivative of this y00 times f22. So this is very straightforward. And when we do the backward propagation, we also need to first dilate the affine gradient map, the affine derivative map, because of the same reason I introduced before. Because when we are using a stride larger than 1, we dropped many intermediate value for the output itself in the forward pass. And when we are running the backward pass, we need to fill those drop position with some zeros, these pseudo gradients, to maintain the shape. And the reason why we need this padding is because when we this padding is to ensure that each let me use this example. This x22 is calculated in all these 4 equations. So when you do the backward propagation, you want to consider you want to calculate the corresponding let me rephrase that. So you need to mind the frequency of each x in these forward propagation, and that could be done by using some padding to control the convolution steps. Because in this case, when you calculate the derivative of this first position, the x00, you only consider this y00 instead of including all other y's. And when you calculate the derivative of this x22, you consider all these y's instead of neglecting any of them. And this is the same as before. We also need to rotate the filter to ensure to simplify the convolutional calculation and to map those to switch the future items to a correct position, because because as we discussed, I think here the relation between the affine output map, this derivative of the affine output map is having some flipping relation with the filter itself. So that's why we want to flip this filter horizontally and vertically when calculating the derivative of the input. And so yeah, here. So let's sum up the convolution. Let's sum up the calculation of the derivative with respect to the input. So first we want to dilate, or we can call it upsample, the derivative map, the affine derivative map with your strike settings, and you need to also pad the output, the affine derivative map with your kernel settings, and then flip the filter horizontally and vertically. And after that, you can just run this convolution calculation we introduced before to get the derivative with respect to the input. And so for the situation where strike is greater than 1, your derivative of the filter is done by doing the convolution between the input map and the upsampled affine derivative map. And the derivative of the loss with respect to the input is done by like running convolution between the flipped or the horizontal and vertically flipped filter and the upsampled output derivative map. That might seem like sounds very complicated, but I believe most of them could be understood after the lecture. And yeah, this is what we discussed before. E/2, like some convolution calculation. You just need to mind like the dilation and the padding happen in this affine derivative map. And I think that's all for the backward propagation part. Yeah.
I mean, I know you have to go soon. So
Yeah.
if anybody has questions, I think I can take them, and unless you want to stay and answer them as well. I will probably have to make a judgment call to either take questions or go through a notebook, which is essentially a playground for you guys. So if you have any super pressing questions, I mean, I guess go ahead and shoot. If not, I think I can give you guys a little walkthrough of the notebook, and yeah, we can take more questions after that. I mean, as I said in the chat, it would immensely help if you create a computation graph for the forward pass, and then just you'll kind of almost immediately see why the backward pass works the way it does. And there's another parallel to be drawn with MLPs and CNNs here, that if you remember, the backward pass of an MLP or any linear layer is essentially doing the same matrix multiplication, just in the other direction. And similarly here, the backward pass of a convolution is again a convolution with some flipping of the kernels, and some padding added here and there. So there are a lot of parallels between MLPs and CNNs, and in fact, you can do what a CNN layer does with a linear layer if you use the shapes correctly, and vice versa. So that's maybe something to keep in mind. Yeah, I guess I'll wait for a minute or two to see if you guys can come up with some questions, because it might be a bit much to digest and questions might not be obvious. In that time, I would encourage you guys to go ahead and open the notebook that we've linked in the description of the Piazza post for this recitation. And in fact, I will link it here in this Zoom chat as well for anybody who doesn't want to go on Piazza. it would be great if you can make a copy of this in your drive and you can go through it at your own pace. All right, so let's quickly take a look at the notebook. And for anybody who likes dark mode, I had to turn it into light mode for ease of viewing. So no hate, please. All right. So there is a bunch of text here, which I do encourage you go through. All of the documentation is largely available online. Stack Overflow is always your friend. PyTorch docs and PyTorch forums are a really good place to find some good documentation as well. But yeah. So essentially what this notebook will do is maybe help you familiarize yourselves with how the sizes of the inputs and the outputs work in terms of convolutions in 1D and 2D. How downsampling works, how you can use convolution layers. If you're not aware of it already, PyTorch has a whole functional API as well, in which you don't have to declare layers and then call the layers. You can simply call the function, which will do it for you. So we'll take a look at that. Of course, there's normalization, dropout. There's also some basic model, which you guys can use here to kind of play around, see what happens. And towards the end, we go through some pre-trained models like VGG16 that you can just import from the magical internet and use them. And of course, last but not the least, we can look at things like debugging CNNs. And this thing mentioned at the bottom, which is called GradCam, is super useful in really seeing what the feature maps are producing. So it's worth going through that paper as well as a very quick read. It's not too long. All right, so not to take up any more of your time, we can just run these cells here. So we'll see that our input image size is a 32 by 32 image. It has 3 input channels, and currently there's only 1 image in our batch. And for the 1D case, we have 40 features or 40 dimensional image, or sorry, signal, and there are 100 time steps, right? This is the same equation that we saw in the presentation today. This is not just a square bracket. This is a floor function, which corresponds to the true divide in Python. And yeah, once we create a layer, we'll see that when we do the convolution, it gives us a size of 28 by 28 out, which you will see because your kernel size is 5. We are not adding any sort of padding. Our input size was 32. And so you'll see that this 28 by 28 makes sense. And this 20 here came because you have 20 output channels. So in PyTorch, the number of kernels, so to speak, is defined by the number of out channels that you define your conv2d layer with. So this kind of makes your whole computation really simple. You define how many channels are coming in, how many channels going out, what's the size of your kernel, and the stride. And of course, there are other parameters like padding and so on and so forth, which you can see in the documentation here, right? So as I was saying, we can see what happens when we pad it. And if you remember that one point about padding, that you can use it to preserve the input size, that's essentially what happened here. So by using a padding size of 2, which we got to by solving this equation to maintain the output width as to be the input width. Oh, there's a little typo here. But yeah, so with a padding of 2, we got the same output size as the input size. Right. This little cell should sort of let you see what happens when you have different padding sizes with the kernel size of 7. I mean, of course, feel free to play around with this as much as you want. I will sort of speed through this because in interest of time, and of course, you guys can go through it at your own pace as you go through the homework as well. Right. So Yeah, here we sort of talk about what upsampling does. So we went from a 16 by 16 20 channel image to a 32 by 32 image simply by dilating our input, right? Oh, image feeds is not defined.
Quick question.
Yeah, yeah.
So for the upsampling that we've been talking about,
Uh-huh.
theoretically, we talk about adding zeros between every row, right?
Uh-huh.
Or say you have an upsampling of one, we talk about adding zeros between.
Yeah.
How is that different than, that feels different than this one, which is upsampling with nearest neighbor or upsampling
Yeah.
with linear?
Mm-hmm.
I don't know. How does that change things compared to the zeros we've been thinking about?
Definitely, I think that's a good question. So zeros tend to be a default choice for adding any sort of irrelevant information into your data. And the reason why we usually choose zeros is we don't want to introduce anything that wasn't already there and something we're not sure of. However, when you do something like nearest or something like a linear interpolation of sorts, you're sort of introducing this assumption that if I expanded my image, this is what would have been there. Whereas putting zeros, and in terms of images, it tends to mean there is no pixel intensity there whatsoever. So in terms of zeros, it represents that we have no idea what's there, so we'll make no assumption and put a zero there. Although you can always argue that that is also an assumption that there is zero. But I think as far as the strength of the assumption goes, adding a zero is probably a pretty safe choice. But of course, it can have effects resulting from, I mean, there being a zero in it. Does that make sense?
Yeah, if someone was making a basic content with PyTorch stuff, do you think it'd be more common to do upsampling with a mode like this or with zeros?
I think it's the most common to do it with zeros because it makes it easy to sort of form a baseline. And then you can sort of change things and see what effect something else has. I guess something to take with a pinch of salt is that all of these factors in any neural network tend to only have a limited effect. So, I mean, I think we have droned about this for long enough, but I can't stress on it too enough about how important it is. But it's always good to change one thing at a time. And in the same spirit, we tend to keep these things as normal baseline as possible, and then change other things on top. And once we're sure of what works somewhere else, we change things which would otherwise be default. Uh, does that make sense?
Yeah.
Right. Sweet. Yeah, I will fix this. I think this happened because I was editing this just a bit before, but yeah, of course. So you can go through the other cells and they kind of just let you see what happens when you upsample or downsample. One thing that you can probably take from this is things like nn.upsample are very rarely used unless you want to explicitly do it, because there are other ways of upsampling simply using convolutions. But it's useful to know that these things exist, right? Similarly for conv transpose as well. And yeah, same thing goes for downsampling. Of course, we can play around with convolution layers. What happened here, I think this is a little interesting. What happened here is by using that output size equation, we sort of created a chain of convolutions or convolution operations, which gave us an output of 1 by 1. And if you squeeze this, or essentially if you remove these dimensions, it will become a one-dimensional vector of 20 feature values. And I won't tell you exactly where this will be useful, but it's good to remember that this can happen, and it'll help you maybe sort of do classification at some time in the future, maybe in a homework, right? So yeah, the reason why we chose kernel size of 5 and kernel size of 28 is so that we can achieve a 1 by 1 here. But something that you might want to look up on the internet is, I think it's called adaptive pool, or it's named something similar to that. Essentially what it does is, in adaptive pool, you specify what's the output size that you need, and it will change the kernel size based on whatever you need at the end. Right? So that's something useful to know.
Just to clarify,
Mhm.
so we can't have different strides or different kernel sizes in the same layer, right? Then, because the way this is set, it needs to be different.
No, you can't. Not by default in the PyTorch API. But you can always, I mean, since you'll be doing it in homework 2 part 1 anyway, you'll be creating your own, I mean, we'll be creating MyTorch. So since that is essentially possible, you can create an API which does that, but it's just that it'll become sort of annoying to deal with because your output map won't be standard anymore. What I mean is each channel that you have convolved with, or each of the output maps that you get through each of the different strided kernels would be a different size. So either you'll have to pad the ones which are small to make them as large as the largest one, and then you can sort of pack it in one tensor. Otherwise, it would be a staggered tensor, which doesn't really look nice because you have different sized things everywhere. Does that clear your question?
Yep. Thank you.
Yeah. All right. Cool. Yeah, I won't touch convolutional functions simply because they're not used much, but they're kind of fun. As I said, you won't have to define a layer and then call the layer. You can just do functional dot that function. Of course, normalization and outputs and dropouts are super handy tools for regularization. Just a quick refresher, batch norm lets you deal with covariate shift, make sure that all the batches that you're training on sort of lie in the same space in the input features, and dropout essentially tries to mimic an ensemble effect inside by dropping neurons and making sure that the network is not learning things which aren't needed for the task. All right. Yeah, so this little section here, which is reading image data. So we have provided you this little drive link here, which you can add as a shortcut to your drive if you want to go through this section of the notebook, that is. And what this section will do essentially is, I mean, we've put images of Beeksha and Tony here. But essentially what will happen is you can load the images, play with them, see what data transformations can do. Of course, you can crop, clip, rotate images, change contrast, everything that you do on your phone when you're editing an image, you can do using libraries on Python as well. They're just a little less UI oriented, so to speak. But these transformations help your model become more resilient or invariant to these changes, which might happen when real data comes in. So this is probably worthwhile to go through. Of course, there's this basic PyTorch model, which might help you get started with homework 2 part 2. Of course, the bootcamp will do that as well. But I mean, more resources is hopefully never a bad thing. Yeah, serialization just typically talks about creating a whole training loop. We sort of left this as an exercise because you've done this in homework 1. You can just sort of copy those things over and it will work out of the box. Yeah, and at the end we go through, as I said, some pre-trained models and some debugging tips. Both of these are of course optional. I mean, the whole notebook is sort of optional, but these are the most optional of the optionals if you want to just keep with the bare bones. So yeah, this is a notebook for you to play with. One thing that I'm not 100% sure of is whether this drive link that I talked about in the, one second, the drive link that I talked about in reading image data is updated or not. So I would suggest hold off for the next 10-15 minutes to using this section of the notebook in case you're super eager to do it. But you can go ahead and add this drive folder as a shortcut anyway, right? Hopefully this notebook shouldn't be too hard to parse if you're going through this on your own. If it is, please feel free to shoot questions on Piazza, visit us in office hours or anything of that sort. Yeah, that's about it. Again, if there are any few lingering questions, I can take them. If not, I guess we can end the session here. All right, that's great. Cool. Yeah, do you have a question?
Yeah, so in terms of the systems design of convolutions, so if a whole row from the image is not possible to fit within caches, within common cache sizes, I guess it will be common within libraries to maybe unwrap the convolutions into different different row operations and then like add it back together at the very end. For our homework 2 part 1, will we be expected to do these optimizations, or can we just, you know, slice out the square that we need and then do Hadamard product?
So for the purposes of the homework, you would not have to deal with distributed computing, so to speak. I'm guessing that's where your question is from. Usually, if the whole image doesn't fit into the cache, I believe the kind of optimization which happens is it takes out like a channel depth chunk of the size of the kernel and does like a one-shot Hadamard product and gets an output instead of slicing out the whole row, because it just makes more sense for the same section of memory to fit in your cache at one point. Right, but you
Right.
won't have to deal with those questions in homework 2 part 1.
Okay, sounds good. Thanks.
Sweet. All right, bye-bye.